So it's a great pleasure to introduce Professor Sébastien Gouëzel from Université de Rennes. He'll be speaking on classes of smooth functions in mathlib, and welcome.
Thank you. Good morning, everyone. Thanks for the invitation. So when you start playing with a proof assistant, surprisingly, the thing which is, in my mind, easiest is to prove a theorem. Say someone has written up a statement of a theorem for you, and then you just have the proof to write. And whatever the way you write down the proof, even if it's ugly, it's not a problem, because if it's accepted by the system, then you know that your proof is fine. And anyway, the content of the proof will be discarded right after that. What matters is that you've proved that the theorem is true. And that's, in a sense, the easiest thing to do. And slightly harder is to write down a theorem statement. You have an informal statement in your head, and you try to write down a statement. And that's a little bit harder because you have some freedom to choose how you will write the theorem. And there are maybe 2 or 3 equivalent ways to state the theorem, but maybe one will be more practical than the other one. So it takes a little bit more practice to write down good statements. And something which, in my opinion, is way harder is to write down good definitions. The reason for that is that the design space for definitions is much wider. I mean, first, of course, you want your definition to be correct and to correspond to the usual mathematical meaning that we give to some object. But even with that constraint, there are many, many ways to implement these things. And maybe you want things to be very general, to allow a lot of applications. And maybe you want things to correspond to the usual mathematical practice. But maybe also you want your definition to be easy to use. And sometimes there is a competition between these different requirements. And so you have to find a balance between all these constraints. And that's pretty hard, in fact. And it takes a lot of experience, but also fiddling with the definition. And you start with some definition to try it, and then you realize the weaknesses. You come back to the definition, you tweak it a little bit, and you do that over and over again until you converge to a good definition. And that's what I want to describe today in one specific example. I chose this example the class of smooth functions in mathlib because I think it's elementary enough to explain in 1 hour, but still shows some of the difficulties. And I could do the same with many other definitions in mathlib, but I think that for a talk, this one is pretty nice. So let me start with some issues with very basic definitions to show a little bit the tension I was mentioning in the previous sentences. So first example of a weird definition in a proof assistant is the division by 0. The definition you will find in books is that it's not allowed to divide by 0. But in essentially every proof assistant, you allow division by 0, and you choose a value 1 over 0 equal to 0. And in a sense, this corresponds to the mathematical practice. When you write down a division in a paper, you do not spend your time every time saying, be careful, the denominator is not 0 because blah, blah, blah. You don't do that. You just write down the division and that's it. And so the choice made in proof assistant that to allow division even by 0 is just for practical use. You don't want all the time to justify that the denominators are non-zero. So just allow division by 0 and pick some arbitrary choice for the result of the division by 0, because in practice, the choice won't really matter. And so in these cases, we call this junk values. Some value that we choose to have total functions to be easy to use, but the value is just junk. We will never use it seriously. Another weird example of a definition in a proof assistant in mathlib, but also in Coq, in Isabelle, in Rock, in Isabelle, that on a paper, when you define a metric space, you will just take distance function with 2 or 3 axioms, and that's it. And in mathlib, the definition of a metric space will include the data of the topology which is compatible with the distance function. And that may seem completely crazy because this topology can be deduced from the distance. But for implementation technical reasons that I don't really want to discuss today, it's important to also include the data in the formalized definition. And in a sense, that's really a technical thing, but that we have to do, because if we don't include that, many things break down pretty rapidly. So in these two examples, the difficulties are, say, tied to the fact that we are using proof assistance. The definition that I'm going to discuss today will look unusual, but the reason will be mathematical this time. And so that's why I think it's pretty interesting. Even if you think that you know perfectly well what a CN function is, maybe you will have some surprises today, and I'll motivate an unusual definition. I forgot to say, but don't hesitate to ask questions. I don't care if I don't get by the end of my talk. Anyway, it's too long, so I will stop at some point, and I don't mind. I really prefer that you ask as many questions as you want. It's especially for talks and videos like that, it's really nicer. Okay, so what I want is to define smooth functions, say C-infinity functions. But before that, I have to tell you a little bit how derivatives are defined in mathlib. So I will first start with the paper definition of derivatives. I take two real norm spaces and a map between these two spaces, and I will say that it's differentiable at a point x is the map locally can be approximated by a continuous linear map L. Very usual definition. And this L is unique, so it's a continuous linear map from E to F, and it's called the derivative of the differential of the map f at x, and it's denoted by, okay, you have a bunch of notation, df of x or dxf, or sometimes f prime of x. If you're in a differential geometry setting, sometimes it's a txf, a bunch of notation for all the same object, continuous linear map. Maybe I should also say that if you are in one dimension, there is a slightly different notion of derivative, which is not a continuous linear map, but just a scalar. And in fact, it's the same because in one dimension, continuous linear map can be identified with scalars just by looking at the value at 1. And in paper math, we do this identification in a completely fluid way. When you formalize things, you have to be careful. So the definition I've written on the board is for general Fréchet derivatives for maps between real norm spaces. If we are in one dimension, we will also have specialized versions interpreting this as a scalar. I won't mention it today. I will do everything in a higher dimension, except in some examples, and then I will do the identification just as we are used to do. Okay, so that's the definition I've written is the first one that you think of formalizing, and it turns out that it's not general enough, because there are many statements that are given in terms of more general notions of differentials. And here, a very simple example, if you have a real function and say that in the closed interval 0 plus infinity, your function is differentiable at 0 with a positive derivative, and then you want to say that for small enough positive x, then f of x is strictly larger than f of 0. So what I'm doing here implicitly is that I'm using not full derivatives, a full derivative in all directions. I'm looking at the derivative in a half line, so a one-sided derivative. And when you do differential geometry, often you have a manifold with boundaries. And when you have manifold with boundaries, it's the same. You cannot differentiate in all directions, but only in the direction of a half plane. So a good definition, a good formalized definition of derivatives will have to take these applications into account. And so you will we will need to formalize not only the notion of derivative, but of derivative within a set. And the reason is that there are a bunch of applications of natural statements that are in terms of this notion. So we cannot avoid it. A good library will have to include this kind of definition. So here is a way we formalize it. So here are some excerpts from the mathlib library, which are not very important. If you are a little bit scared of the syntax, it's not a problem. I mean, my talk will, you won't need to look at the details of the syntax. So we include a few predicates. The first predicate has f therein within at, where f stands for fresh air, say that some map f has within a set S a derivative f prime at a point x. And the definition is exactly the one I told you before, that the difference of f and the linear approximation should be negligible with respect to the difference between the points. And once you have this predicate that f has a derivative f prime within the set S, we'll say that the function is differentiable within this set at a point x if there is some derivative. There exists some f prime such that we have this predicate has f derivative within at f prime is x. And now comes a little bit more tricky definition, because it's very good and nice to say that we have some derivative, but often when you want to compute, you want to put your hand on some derivative. And here in this kind of setting, there is no guarantee that the derivative would be unique, but still, to Ryan thinks it's very convenient to have some choice of a derivative. So we introduce a choice of the derivative like that. It's called f deriv within of the function. So you give it the field, the function, the set, and the point. And you get a continuous linear map from E to F. And how is that defined? Well, first note that in this definition, we are not assuming that the function is differentiable. So just like we were allowing division by zero on the previous slide, here I will be able to write what the derivative of a non-differentiable function will be. And it's just for convenience. I want to be able to write f derivative within of some function without having to provide all the time a proof that the function is differentiable. And that's a junk value here. It's zero. It's if the function is not differentiable, okay, pick the junk value. And if the function is differentiable, it means that there exists some derivative. And so what we will do is pick such derivative. And that's what the classical dot choose h is doing here. Pick some derivative if we know that there is a derivative. But then there is something more. You see that there is these lines above that if I can pick if my function is differentiable and 0 is one of the allowed derivatives, then I will pick this one. Okay, and here that's not a junk value; it's a convenience value. We could get away with this one. We could get away with, okay, if there is some derivative, pick it, and otherwise pick 0. But it turned out that tweaking a little bit the definition like I did gives you a better behavior for some theorems. It has no bad consequences, but it has better behavior for some theorems. For instance, a theorem which is true with the definition I've written, but would be false with without this convenience value, is that in one dimension, the f derivative within of a function is always measurable, whatever the set S, even if S is the empty set. It may seem crazy. Okay, if S is the empty set, then you have nothing to check here, because points cannot converge while remaining inside S. So yes, there is a question.
Yeah, I just since you're talking about these particular choices, there's this thing that people do in programming languages to partially deal with this junk value case, which is this idea of a raising exception, which you probably know from Python and so forth. Has that been considered to put into Lean?
Okay, there is a way to do that, but in a mathematics setting, raising exceptions does not really make sense.
Well,
So
it might, because it's again, but it's not that you just can ignore the exception or say this proof broke down or something. It's to say that there's some kind of more global way, within this block of code to deal with all the exceptions.
okay, I'd say there are two answers to this. One answer is that you can take advantage of the type system to make sure that you will never raise an exception, because you will always pass to your function a well-formed data where you won't need to raise the exception. And that would be exactly a function f derivative within, but without junk values, but which would take an argument that the function is differentiable at the point you're looking at. And can definitely be made, except that it's not really convenient, because, as I said, when we're using this function, it's a pain to always feed in the proofs of differentiability.
Well, I guess the other mechanism, which isn't lean, is to say like fact, fact A is greater than 0 or something, right?
You could pass this assumption as a fact, but when you're applying this to complicated functions, the system would not be able to check these facts by itself. So that's one design we have tried. And for this kind of derivatives, it didn't work out well, because when you start having complicated functions, the system was not able to check the differentiability all by itself. So junk values,
to bring these ideas up,
and exceptions are important when you want to compute something, when you want to run your program. But in fact, when you're doing mathematics, you don't want to run your program, you want to prove things about them. And then it turned out that the design I'm describing turned out to be more convenient. It's just some experimental facts.
Right. Okay.
On the other hand, for instance, when you want to program the interface with lists, you want to get some element of a list at position n. And then if n is longer than the length of the list, you can do several things. You can either panic, or return a value which is the default value of your target type.
Well, again, there's this third case where the exception might be useful, where there's a bunch of ways that your assumptions can fail, and then for any of those ways, like in differentiation, you say there's no derivative, and so you have this common kind of. But
here.
Okay. We discussed it.
So with this convenience value, turned out that if you look at f derivative within of at an empty set, any continuous linear map would be a derivative, but this convenience value will take the value 0, which means the derivative will always be 0, and the constant function 0 is measurable. So this slightly weird definition ensures that some more theorems are true at no cost. In fact, the first definition we had of f derivative within did not include the convenience value, and we converged to this one after several versions of the definition. It turned out that this one is extremely convenient, but it wasn't our first choice. It came after several iterations. And now I can tell you this one is really convenient to prove theorems. Of course, it's not something that you can run. Well, it's not something that you can run because first there is an axiom of choice here, so it's not something that the program can do. And anyway, giving some arbitrary function between two real norm spaces is not something that you can put in your computer. So those are not things that you can program, that you can run. These are things that you can prove properties about. Okay. So there is a difficulty that I quickly mentioned before, that derivatives within sets are not unique in general. If you have the derivative in the whole space, of course it's unique. If the map is differentiable, the derivative is unique. But if you have a set which is too thin, derivative typically is not unique. And here is a silly example. I'm defining two maps from R2 to R, and the first one is L of xy just x, and the second one is m of xy is x plus y. And these are linear maps, so of course they're differentiable, and the derivatives is just themselves. dl is just L, dm is just m. It's an m here, sorry. It's an m. Sorry. And so that's if you differentiate in the whole space. But if you just consider these two maps on the horizontal lines, r times 0, then these two L and M, they coincide on the horizontal line, r times 0. And so the derivative of L within this horizontal line, at any point, it could be L or M. Both work out fine as derivatives, because you're only moving along the horizontal line. So what's happening in the transverse direction is relevant. So the definition made on the previous slide using the choice function, the axiom of choice, maybe at some point it will pick L, and at some other point it will pick M, and in a random way, in a non-measurable way. So this function f derivative within, it can be extremely bad, even if the function is very nice. In domains which are not thick enough, this function can be badly behaved. Okay, that's a fact of life, and that's not really a problem, but that's something you have to keep in mind. Many statements will not be true because of this lack of uniqueness of derivatives. And so we introduce some predicates to say that some sets are nicer, some sets have unique derivatives, and we call these unique diff within at. At some point inside the set, derivative has to be unique, and unique diff on. At every point inside the set, the derivative has to be unique. And once these predicates are satisfied, then f derivative within is well behaved. Otherwise, don't trust it to be well behaved. And here is, for instance, the kind of theorem we can have. F derivative within add tells you that the derivative of f plus g within set S at the point x is the sum of the derivative of f and of g at the point x. And for this, you need assumptions. And the assumptions you need are first that the functions f and g are differentiable within S at this point x, and also that the set S has unique derivatives at this point x. Otherwise, the theorem is just not true because I gave you a counterexample above. So whenever I write down a theorem like that on the slide, it's a theorem which is taken straight from mathlib. So there is a proof in mathlib that I won't show you because the proof is not interesting at all. It's essentially trivial. But it's just to show that the definitions are engineered well enough that they make it possible to prove theorems. And that's the main test for definitions. If you're trying to prove theorems with your definitions and you're not able to prove the theorems, maybe the definitions are not good ones. Okay. So now I want to go to higher smoothness. So higher smoothness, I take two real norm spaces E and F, and I consider some function f from E to F. And I want to define what's a Cn function. For n equal to 0, we know what this is, it's just continuity. F is C0 if it's continuous. And for a positive number n, we will say that f is Cn if the function is differentiable, what I defined on the previous slide. And if it's differentiable, and here I'm talking about the whole space, so there are no issue, I can look at the derivative. And the derivative df, it's a map, taking a point in E and mapping it to some continuous linear map from E to F that I denote by this calligraphic L of E and F. So df, it's a map from this real norm vector space E to this real norm vector space L of EF. It has a norm, which is the operator norm. So since it's a map between real norm vector spaces, and I'm doing some inductive definition, I can use my definition at step n-1. So I will say that f is Cn, it's differentiable, and the derivative is Cn-1. And finally, we say that f is C infinity if it's Cn for all n. And that's the standard definition, standard inductive definition of a CN function. Maybe I should say that there are also sometimes definitions in terms of partial derivatives in all directions, and it's a definition I like a lot less than the one I've written on the board, because it only works in finite dimension and it requires a choice of a basis. So it's from a mathematical point of view, it's less convenient to work with. And also from a formalization point of view, it's combinatorially much more heavy to use. So I'll focus on the definition I've written here, which is well, more general. And as I told you, in mathlib, we want to have general definitions to apply them in as many situations as we can. Okay. Something that I should say is that if you take this definition and you think that of a C2 function, so the derivative f is a map from E to L of E to F. So if you differentiate that, the second derivative, it becomes a continuous linear map from E to a space of continuous linear maps from E to F, which is a slightly messy space to work with. But what does that mean? It means that a function like that, it can eat a vector in E, and then you get a continuous linear map. So it can then eat a second vector, and you send it to a point in F. So you can think of this as a function taking two arguments, two vectors in E, and giving you an element in F. So you can interpret this as a continuous bilinear map, which is more convenient to use. And this step is standard and called uncurrying. And that's the same way for the nth derivative. If you take the definition I've written on the nose, it's a continuous linear map from E to the continuous linear map from E to blah, blah, blah. That's a mess to use. But this space can be naturally identified with a space of continuous n multilinear maps from En to F. And so the iterated nth derivative, it's usually seen as a continuous multilinear map. And that's what we do all the time when we use them on paper. And spoiler, when you formulate things, you will have to be careful about this. But the intuition we want to have is really, well, not just the intuition, the formalization. We want to see the nth derivative as a continuous multilinear map, just to be able to use them, to write on formula, to feed them vectors, and let them spit some vector in the target space. So that's what we want to have, and that's what we will get. So the paper definition I've written is very nice, but as before, I told you, naive definition of derivative is not good enough because it did not handle derivatives in domains. And here it's the same. This standard paper definition has several weaknesses. And here are a few limitations of the definition I've written. I've written it over the real numbers. Of course, we also want to have a smooth harmonic function with respect to complex numbers C, but also with respect, say, to other fields. For instance, with respect to the p-adic numbers, there are deep theorems that talk about p-adic manifolds. So if you think in advance that someday you will need to formalize p-adic manifolds, already know you have to think, okay, I have to be careful. My definition should take these future applications into account. So I want something more general. I want a more general field of scalars. Another limitation is that it's only written in whole space. But already for the first derivative, I told you there are many natural statements where you cannot differentiate in all directions. You need to be able to take of C1 functions in domain or Cn functions in domains. You want to, one day we will formalize Perelman theorem. One day, maybe. And for that, you need hyperbolization. You need to glue together manifold with boundaries, three manifolds with boundaries. So manifold with boundaries have to be one primary target you have to keep in mind. And so you really want to be able to talk about Cn functions in domains. And then another limitation, which is maybe less obvious than the two I've already written, is that when you want to know the right generality to formalize things, often what you can do is open books by Bourbaki, a famous French team of mathematicians, because they've really thought a lot about what the right generality is. And they have a book on manifolds, and in this book on manifold, from the start they say we will study manifold of class Cn for n which is either a natural number or infinity or omega, and where C omega means analytic functions. And they say from the start, when the field is not R or C, we will only look at analytic manifolds. So what does that mean? Is that if Bourbaki is right, and often Bourbaki is right, and if you want to get some general theory of Lie groups, encompassing both real Lie groups and Lie groups over QP, then you better have in your scale of smooth functions the analytic functions. Because otherwise, you will do some theory of real Lie groups where you do it in C infinity, and then separately from that, you will do a theory of analytic Lie groups over QP, and you will have to reprove everything twice. The developments would be copied one from the other, and every nice theorem would have to be stated twice, and that would just be a pain. And it's much better to have to build your theory to have just unified statements that cover all the cases of interest. And so if you believe in Bourbaki, better include analytic functions in your scale of smooth functions. Okay, so I'll try to describe the definition we have currently in mathlib that will solve these three issues. So yeah, the suitable definition of Cn functions in mathlib should solve simultaneously these three difficulties. That's something we need if we want to have a comprehensive library to cover all possible applications. Of course, if you're doing one single project focusing on one specific theorem, you don't need to think of this huge generality. But if you're building a library that should apply to many separate projects, you should think of a definition that will also be suitable for everyone. Okay, so let's try to formalize Cn functions and see what goes wrong with the naive tries we could do. The first try is that we could follow literally the paper definition. We could say, okay, I know how to define the derivative function. I showed you the function f derivative within before. So I could define inductively the nth iterated derivative of f within the set S as a derivative of the n-1th iterated derivative. And once you have that, you could say that f is Cn within S if all these iterated derivatives are well defined and continuous up to stage n. Okay, that's the definition. And this definition has a very bad issue that I told you that even if the function is very nice, I took the linear map L of xy equal to x. If the domain is R times 0, the f derivative within might be very bad. I showed you an example where, since there is this use of choice in the definition, the derivative within S could oscillate between the maps L and M. It could be non-continuous, even non-measurable. So this function possibly is not C1 on R times 0, and that's really bad because this function is C1 on the whole space, and you want to say, okay, if I'm C1 on some set, I take a smaller set, I'm still C1 on this set. And that wouldn't be satisfied with the definition I've written. So that's a bad definition. And the reason that's a bad definition is that it's written in terms of this function f deriv within, which is using choice for the definition because of non-uniqueness of the derivatives, and so choice might be a bad choice here. So if you want a good definition, you should not rely on this function defined by choice. You should do something else. And instead of asking that this specific choice f deriv within is good, it's better to ask whether there exists some nice sequence of iterated derivatives. So let me do a second try. I could say that the function is Cn on this set S. Note that I'm not talking about C omega yet. It's gonna come later, but first I'm focusing on the case Cn for n, a natural number or infinity. You could say that the function is Cn on S if there exists a sequence Pm of x of multilinear maps such that P0 should be your original function. I forgot to write it. And P0 equal F. So you want to have a sequence of multilinear maps where the first one is your function, and then it has a derivative P1, which is continuous, and which has a derivative P2, which is continuous, and so on. So it makes more sense than the previous definition. Instead of asking that the specific choices f deriv within are nice, I'm just asking that there is some nice sequence of successive derivatives which are continuous and differentiable on the set. So here is one formal bit that helps formulate this sketch of definition. I have a function f. I have this p, which represents the sequence pm, which this formal multilinear series KEF means a sequence of m multilinear maps for all m. And so I will say that f has this sequence Pm as a Taylor series up to n. If first, at step 0, P0 coincides with f, and then at each step before n, Pm has Pm plus 1 as a derivative. And you see that there are this curry 0 and curry left here, which are the inconvenience that linear map into continuous linear maps with n variables are not the same as continuous linear maps with n plus 1 variables. There are these identifications that we do all the time in our mind, and here you have to write them down. But okay, you have to write them down to get some. Yes.
There's a question in the chat.
Yes, sorry, I don't see the chat. I don't see the chat. Can you ask the question, because I don't see the chat here?
Yeah, I can ask it. So should m be strictly less than n in the definition?
Should m?
I think you've written. Yeah, I think you've written that in the lean code, but not above. So I think it's fine.
Okay, there exists a sequence Pm for m less than or equal to n, and the condition Pm plus 1 is a derivative of Pm should be for n strictly smaller than n. The condition on the being a derivative should be for m strictly smaller than n, but you need the sequence up to n, at least if n is a natural number. Thank you, you're absolutely right. So that's it. And there is also a continuity condition, because we're talking about Cn function. So if n is a natural number, you want the last derivative to be continuous. And that's the role of this last condition. And if n is infinite, there is no condition at all, because all the previous ones are automatically continuous because they are differentiable, because they have a derivative. Anyway, so this structure is a way to formalize the equation I gave above. And there is still an issue with this definition. And the problem with this definition is that it's not a local definition. It's not local in the smoothness, and it's not local in space. What do I mean by that? With this definition, you could have a function which is Cn on S for all n, but which would not be C infinity. And what the reason is that maybe your function is C3. So you have a sequence P0, P1, P2, P3, which satisfy your axioms. And your function is also C4. So you have another sequence Q0, Q1, Q2, Q3, Q4, which satisfy the axioms. But maybe they're not the same because there is non-uniqueness. And so if your function is Cn for all n, but the derivatives given by the definition do not coincide, you cannot glue them together to form a sequence of derivatives that works for all n. Of course, if you're on a set with unique derivatives, derivatives are unique, they will have to coincide, so you can put them together and show that a Cn function for all n is infinity. But if you don't have a set of unique derivatives, it's not clear. In the same way, you don't have a special locality in the following sense. If you have a function which is Cn around each point, it might not be Cn on the whole set S, because maybe the p's you get depend on the base point, and they don't match on the intersections of the set where they're defined. If they match, you can glue them together and get something that works fine. If you're over the reals in finite dimension, you could use a partition of unity to put them together. But if you're not in finite dimension, and if you're not over the reals, you don't have partitions of unity, you cannot glue them together and you're stuck. So if you want a nice definition that works in all situations, you have to take care of this locality issue. So let me solve the locality issue by forcing the locality in the definition. So if n is a natural number of R infinity, I will say that f is Cn within S at some point x, if for all natural number n prime smaller than n, there exists some neighborhood of x and a sequence of multilinear maps, and this neighborhood such that Pn plus 1 is derivative of Pn within S. So this definition is locally just at a point. And then I will say that f is Cn on S if it's Cn within S at x for all points in S. Since the definition is local by design, it globalizes. I mean, if by definition, if you're Cn locally at each point on your set, you're Cn globally on your set, because that's the way you define the things. So that's a trivial and stupid way to fix the previous issue, but it works fine. So this definition is nice. It works fine. If you write on this definition and try to prove all the standard properties of Cn functions, you're able to prove them with this definition. So it solves the locality issue, it solves the lack of uniqueness issue, and it works fine for n in natural numbers and infinity. So now let's go to C omega. What about C omega? Wow. Okay, first try, natural try. We could say that f is C omega within S at x if it's analytic there. I mean, there is a converging power series converging inside S, inside the neighborhood of x in S toward the value of the function f. And I should say that analytic functions were already in mathlib before, so I'm free to use them to give this definition of C omega. And there's a problem here that, okay, I've written nonsense, but still, I've written that an analytic function at a point doesn't have to be C1 there, which is true which is true if the target space is not complete. That's crazy, but you can have a function which is given by a converging power series. So when you're given by a converging power series at a point, then of course you'll see one at this point, but maybe you're not analytic at nearby points, because your series, which was converging at the initial point, when you move a little bit, you get a new series. Maybe this series is not converging if the target space is not complete. That's really strange, but that's a fact of life. So we could require that all our spaces are complete. In general, analysis or geometry work much better if spaces are complete. But until now, completeness was not needed anywhere. So it would be a little bit weird to introduce this assumption, which apparently wasn't needed at all to talk nicely about Cn functions. And why do I say it's a problem? I want to say that a C omega function at a point is a C1 at a point. I want some, in this scale of smooth function, I want some monotonicity with respect to the exponent. Yes, that's what I've written. If m is smaller than n, I want a Cn function to be Cm, of course. That's one of the theorems I want to have. So I have a slide with an example of a function which is analytic but not C1. But since well, it's not really exciting, so we'll just skip it. But if you want to have a look, you can have a look or ask questions later. So how will I solve that? Well, again, in a stupid way. I'll solve that by tweaking the definition. I require that the function is analytic. Sorry, C omega and analytic are not the same. I will say that the function is C omega if it's analytic, but it has also a sequence of successive derivatives in the previous sense with this as F Taylor within R. So it admits some sequence of successive derivatives which are also analytic. In a sense, it's cheating. But with this definition, C omega will imply Cm, because in particular, a C omega function has a sequence of successive derivatives, so it's also C infinity. So coming back 1 second. Okay, and now I think we've solved all the major naive issues that we had. So I can show you the formal definition of Cn function inside a set that we have in mathlib. This definition is copied from mathlib. And it's really taking what I've just explained and putting it into symbols. So it's cont diff within at for differentiable and continuous. And initially it was called times cont diff within at because it's several times continuously differentiable, but it was just too long and we brought the times. So the name is a little bit weird, but we couldn't come up with a nice name, which was short enough. So it's called cont diff within at. So we specify the field K, we specify the smoothness, we stop n infinity, which means that it can be either a natural number or infinity or omega. And then, so the smoothness exponent n, the function f, the set, and the point. And what will be the condition? If n is a natural number or infinity, we require that for every smaller natural number m, then on a small neighborhood, we can find a Taylor series up to this step m. And if the smoothness exponent in omega, we require the same, that there exists a sequence of derivatives, and all the derivatives are analytic. So you see, this really the direct translation in lean terms of the definition we had before. There is no technical trickery. It's a plain translation of the mathematical idea we had, but this mathematical idea we had to tweak it a lot to have it general enough, to to all the applications we want. And once you define what it is to be CM within a set at a point, you say that the function is condiff on, so Cn on a set if it's Cn at each point of the set. And we also define global versions, condiff at, where the set is a whole space, and condiff the function is globally Cn. So, okay. So that's the definition I wanted to show you. And took some time to arrive to the definition. And now let's hope that the definition is okay. And as I told you, the judge for the correctness of a definition is whether you're able to prove theorems with it. So let's browse a little bit through some statements in the library to check that that indeed we can prove some theorems. First, we can prove monotonicity with respect to the smoothness exponent. If a function is Cn and you have some smaller exponent m, then the function is also Cm. Okay, good for us. That's a property we want. If we hadn't been able to prove this one, it would have meant that our definition was wrong. With this definition, this one is okay. Another thing, there was this weird game that if the space is not complete, I had to require that the function was analytic, but also it had a sequence of successive derivatives which were also analytic. Okay, if the space is complete, this issue disappears, and being, say, omega is equivalent to being analytic. So it's a good sanity check. Another one. If you have an exponent which is not infinity, then a function is Cn at a point within a set. If you can find a sequence of derivatives on some given neighborhood of this point, and if the smoothness exponent is omega, then all the terms in the Taylor series should be analytic. So that's one of the characterizations of smooth functions we have in mathlib. And then you may wonder, but why this condition that n is not infinity? Well, because for n equal to infinity, it's not true. You have to think a little bit, but think of a functions, real function, which around 0, it's exactly Cn on the interval -1 over n, 1 over n. Okay, and so when n is larger, this interval is smaller around 0. It shrinks around 0. And then there is no neighborhood of 0 where the function is C infinity. Still, with our definition, it's C infinity at 0, because for any finite n, it's Cn on some neighborhood. But there is no neighborhood where it is C infinity, so you see why we need this condition in the statement. Okay, another version, well, very much related to the previous one, is that the function is Cn plus 1 locally, if and only if it has a derivative which is Cn. And this requires n to be different from infinity, and if n is equal to omega, the function should also be analytic. So all these ones are pretty straightforward. Well, not always straightforward, but at least they're true with our definition above. Okay. Another crash test for the definition is that the addition of two Cn functions is Cn, and that's fine. And I will just skip this because I would like the 3 minutes remaining to talk one application that was a big motivation for this general definition, which is Lie groups. Because okay, CN functions, I'd say they have two big domains of application, analysis and geometry. I'm more into geometry, so I will talk about a geometric application. I'd like to define the Lie algebra of a Lie group. And there are several definitions of the Lie algebra of a Lie group, but one way is to go through the Lie bracket of vector fields. So how do you do that? First, you define the Lie bracket of vector fields on a vector space. And here, you just take a formula. If you have two vector fields V and W in a vector space, on a real vector space E, in fact, it doesn't have to be real, on some vector space or some field, you can define a Lie bracket as the derivative of W, which will be a linear function from E to E. So you can feed it the vector V of X and get a new vector. And so you can look at dW of X applied to V of X minus dV of X applied to W of X. Gives you a new vector. And okay, that formula might seem pretty artificial, but that's a good definition. And why is that a good definition? It's a good definition because it's invariant under diffeomorphisms. Here is a precise formulation of this. If you have a C2 function, then the Lie bracket of the pullback of two vector fields V and W over some map F. Oh, yes, question.
Yeah, what is this? What is the pullback of a vector field under a C2 function?
Okay, let's say that the derivative is invertible.
What?
The differential is invertible. F star V of X, it will be, you look at the vector field at the point F of X, and you pull it back by the inverse of the derivative of X.
Oh, so you're assuming more about F than just that it's a
Yes,
C2
yes,
function.
I'm assuming that the derivative is invertible.
Okay.
In practice, when you formalize it, you will use a junk value idea, and you will say, okay, if the derivative is not invertible, just say that the pullback is 0. But of course, you will only apply this when a derivative is invertible. Okay, so that what I've written above. Okay, so say pullback under a local diffeomorphism. And so pullback and Lie bracket commute, and that's a standard fact, and that's the fact that explains why the notion of a Lie bracket is interesting. And what does that mean? It means that on a manifold, you can also define the Lie bracket of vector fields. Because just look at it just compute the Lie bracket in one chart or another chart, it will give you the same result because of this equivalence property. So it's well defined also in manifolds. Except that if you look at the slides, I've written something weird here. If a C2 function f has symmetric second derivatives. Come on, every function has symmetric second derivatives. Well, if you do the computation here, you see that there is a term involving the second derivatives, and the pullback of Lie bracket will be the Lie bracket of the pullback only when the second derivative is symmetric, not the computation. And so it means that if you want to define the Lie bracket of vector fields in a manifold, you need that the change of coordinates, well, you have two charts and you compose one chart with the inverse of the other one. These will need to have symmetric second derivatives for the bracket of vector fields to be well defined. Okay, so a consequence of that is that if you take a Lie group, by Lie group I just mean a manifold with a multiplication and an inverse map, and they are smooth. You take a Lie group, and then I will define a Lie algebra structure on on the Lie algebra. You look at the tangent space to your group at the identity, call it frag G, and then I define a bracket on this tangent space in the following way. You take two vectors in your tangent space, V and W. You extend these to left invariant vector fields by pushing them by left multiplication under elements of the group. This gives you two vector fields on the whole Lie group. You can take the Lie bracket of these two vector fields. It's a new vector field. It turns out that it's still a left invariant vector field, and you look at its value at the identity of the group. So it gives you start from these two vectors V and W in the tangent space to the identity, and you get a new vector, which is, by definition, the Lie bracket of V and W. And this Lie bracket will satisfy all the properties of a Lie algebra. I mean, antisymmetry, Jacobi identity, and that's it, I think. And why is that so? Because Lie brackets of vector fields always satisfy this property. This is completely formal. You can just check them in, say, in vector spaces using the formula, the explicit formula for the Lie bracket I've written on the previous slide. So, of course, I wrote on the previous slide that Lie bracket of vector fields is well defined when changes of coordinates have symmetric second derivatives. So that's still an assumption in the theorem. So a standing question here is, when are second derivative symmetric? Well, over reals or complexes, C2 maps always have symmetric second derivatives. That's a very basic theorem in calculus. And the proof is also very simple. You look at f of x plus tv plus tw minus f of x plus tv minus f of x plus tw plus f of x divided by t squared. And you do some Taylor expansion, and you check that this converges to a second derivative of f at x applied to v and w. And since this expression is symmetric in v and w, you pass to the limit and you get that d2f of bw is the same as d2f of wv. So that's really simple over RRC. So what I said on the previous slide will apply to, say, C2 manifolds over reals or complexes. Another example is over any field, well, not really known field. Analytic maps have a symmetric second derivative, again. And why is that so? It's because an analytic map is locally given by some converging power series. And you can compute explicitly the second derivative. And the second derivative is a symmetrized version of the second order term in the power series. In the power series, you have a quadratic term, P2. And the second derivative is P2 of VW plus P2 of WV. So it's symmetric just by the formula. And there is some bad news then, that if you're not in one of these two situations, second derivatives are not symmetric in general. For instance, of a QP, there is a infinity function from QP squared to QP, for which second derivatives d2f over dy dx is 0, and d2f over dx dy is equal to 1 everywhere. That's a nightmare, but that's also a fact of life. So, I'm already really late. You should, okay, so I'll just drop the example and just say that, so I formalized in lean the two statements that over the reals, C2 maps have a symmetric second derivative, and over any field, analytic maps have symmetric second derivatives. And so you can put these two together to get a statement in terms of a minimal smoothness that will depend on the field. I want to define some function mean smoothness of Kn, which will be equal to n if the field is R or C. And if the field is not R or C, I want this mean smoothness to be omega. I'm listening to Bourbaki. Bourbaki told me, if the field is not R or C, don't try to do something crazy. Just look at C omega functions. I'm doing what Bourbaki is telling me to do. And then under these assumptions, under these smoothness assumptions, second derivatives are symmetric. It's proved separately over R or C, and for analytic maths, following essentially the proofs I've given on the previous slide. And then once you have that, you can formalize the Lie algebra of a Lie group in a unified way. Don't really look at the statement because it requires to know a little bit the language of differential geometry in mathlib. Maybe you were all at Patrick's talk last week and you remember perfectly well. If you don't, it's not really an issue. But what the theorem here is saying is that if you have some Lie group G over some field K, and if it's C3, if the field is R or C, and if it's analytic otherwise, then the tangent space to the identity is endowed with a Lie algebra structure. So it's a formalization of the sequence of theorem from the previous slides. And that's a unified version. And it means that after that, when you develop Lie group and Lie algebra theorems, you can do it just in one way. You don't need to do separately a theory of R or C on one side and the analytic theory on the other side. You can do just one theory, one size fits all. Okay, I'm already super late, so let me conclude. My conclusion is that there are two ways to get good definitions when you formalize things. The first ideal way is you see what is going to go wrong from the start. You think you are very clever, you think a lot, you anticipate all the difficulties, and then you get the definition right from the start. That's the ideal world. And then there's the real world. And in the real world, you think a little bit and you cook up a definition, and the definition looks pretty good because you're able to prove some theorems with it. And then much later on, when you do more complicated applications, you realize that there is a flaw in your definition. It's not generally enough, or maybe you get something very slightly wrong. And as I said, you discover it much later. And this forces you to revisit the definition and to fix all the files that were depending on the definition. And that's what happens all the time. So the second way, it involves something that we call refactors, which is you have to fix a definition and then you have to fix everything that depends on the definition. And that's just life. It takes some time, but this time is well invested because after it means that your library is better. The definition applies to more situations. You have improved your library. And that's something that ambitious library has to do. It's not one thing that is set in stone. It's constantly evolving, and the old definitions are all the time improved to cope with the new applications. So mathlib is driven by the new applications, and it works pretty well. Thank you very much.
Okay, thank you very much for the wonderful talk. Let me stop the recording, then we'll see if there are any questions.